Hello and welcome to this presentation for the Aerospace Industrial Benchmark of Fault Detection. Let's get right into it. In this competition, we were asked to look at an aircraft elevator, typically located on the rear of the aircraft on the horizontal stabilizer, like on this KLM A330. Especially, we were asked to look at the oscillatory fault case in the servo loop control of the elevator. These oscillatory faults, if they go undetected, can cause excessive loads on the control surfaces and the surrounding structures. These loads need to be considered in the structural design, thus adding additional weight to the aircraft, unless we can consistently detect and pacify these oscillatory faults. By guaranteeing fast detection of these faults, already at a low amplitude, much of the additional weight can be prevented with a purely software-based solution. But oscillatory faults are especially hard to detect. They are zero mean, such that the effects don't add up over time, and they oscillate fast, such that the response of a detector needs to be quick too. In this presentation, I will discuss our solution to the detection of these oscillatory faults, which is based on a sliding mode observer. In previous work on fault detection, Riccardo Ferrari and I have already designed such a sliding mode observer-based approach to detection, which seems to tick many of the required boxes. This method allows for fast detection due to the fast dynamics of the sliding mode observer. Furthermore, with the detection method we designed, it can be guaranteed that there are no false detections. And simultaneous to detection, the fault can also be estimated. So, we decided to apply this same approach to the new system. To do this, first we need to take a look at the system definition. We consider the aircraft elevator servo loop control, where the flight control computer sends a commanded current to the actuator. This actuator moves the servo rod, and the servo rod then drives the control surface. Furthermore, the servo rod deflection is measured and fed back to the flight control computer. This system is modeled as follows, and please don't start to read the whole thing. I will highlight what you need to know. This model contains the dynamics of the servo rod deflection, denoted by P. First of all, we can all see that this model is nonlinear, most apparently due to the square root containing almost all of the terms. Secondly, the model contains multiple lookup tables, denoted by the small k's. Furthermore, the rod position is measured and fed back, causing measurement uncertainties to be present inside the state equation of the model. Next to that, a part of the parameters present in the model is unknown to the detector, but bounds on these parameters are provided and can be used. Lastly, the system is corrupted by faults from the oscillatory fault case. These faults can occur in two places: in the current coming from the flight control computer and in the rod position sensor. Furthermore, these faults can range in frequency anywhere between 1 and 10 Hz, and the fault can also occur in different types. The fault can be so-called liquid, if the fault is added to the existing signal, or solid, if they simply replace the existing signal. And lastly, faults can also have a bias. The competition asks us to consistently detect all of these faults within 3 periods of oscillation. Now, don't bother remembering all these fault types, just remember that they are diverse, and we will come back to all the varieties when we get to the results. The fault detector has access to the reference control surface deflection and to a measurement of the actual control surface deflection. Based on these signals and some model information, the detector will execute two main steps. First, a sliding mode observer is used to generate a residual, which is designed to represent the fault. Then, this residual is compared to a threshold, and if the threshold is exceeded, a fault is detected. As you can see, this is a complicated system, but we can simplify this model to just show what we need to know. And that is that there exists a model of the servo rod deflection P, split up in a part that we can model in the detector based on the available knowledge, a part due to the parameter uncertainty, a part due to the measurement noise, and a part due to the fault. Although we know such a model exists, we would not know what each term is. We can, however, calculate a bound on each of these terms to then finally bound the model itself. And this is all the information we need in order to design our sliding mode observer. A sliding mode observer uses a linear error correction based on the measured observer error, as well as a switching one to force the observer error to zero. The switching term will be denoted by nu.
The observer error dynamics can now be denoted as on the slide.
In an ideal situation, without measurement noise, it is proven that the observer error goes exactly to zero. Substituting this zero, we can see intuitively that the switching term nu will start to estimate the fault with some uncertainty. However, using nu directly will not give us any information about the fault, as it is a switching term which can only take values that we designed. Therefore, we need to filter nu to get a useful estimate of the fault. With measurement noise, the same intuition holds, but the estimation uncertainty will increase and, more importantly, will become much harder to quantify. Luckily, we have done exactly this in our previous work. With measurement noise, instead of the observer error going to zero, we know that the difference between the real observer error and the measured observer error is bounded. Furthermore, instead of E dot going to zero, we can bound this rate of change of the observer error. And we know when the observer error is going up and when it's going down. Based on this, we can calculate a bound on the residual in healthy conditions,
which will then become the threshold for fault detection.
With this design, we implemented the observer and the accompanying threshold on the oscillatory fault case in the elevator servo. But it turned out that this approach is too slow to provide detection in the region with higher oscillation frequency. And this turned out to be mostly due to the filter which is required to get a useful residual from the switching term. So after this setback, we decided to rewind a little bit. Because before the residual, the fault already affects the observer error dynamics. And maybe we can use this effect directly so that we circumvent the filter. Now we still have the bounds on the observer error dynamics that we had before. So we'll try to combine those into a bound on the real observer error E. And this is shown best through a drawing, where we start with an initial measurement of the observer error. This measurement represents the real behavior of the system, whether it's healthy or faulty. And we know that the real observer error is bounded somewhere around this measurement. Then, towards the next measurement time, we used the bounds on E dot, which we modeled based on the healthy system behavior. As the measured observer error is positive, the observer error will go down. Furthermore, the rate at which this happens is bounded. And this gives us a new bound at the next measurement time. At this next measurement time, of course, we also get a new measurement with its corresponding bound. We can now combine these two bounds to get a tighter bound on the real observer error. And this bound can be calculated at every new measurement time.
Denoting under bar E as the lower bound on E and upper bar E as the upper bound on E,
we now have this condition, but we don't know the real observer error E. So this is not a condition which we can directly check for fault detection. So we have one more step to make. And in this step, we just get rid of E, leaving us with a very logical condition that we can easily check. The lower bound on E is lower than the upper bound on E. Furthermore, this condition can actually cause detections, as it is influenced by the real, faulty system behavior through the measured observer error, and by the modeled bounds on the healthy system behavior through the bound on E dot. If a fault occurs, the real and model system behaviors will contradict each other,
and therefore this condition might no longer hold in a faulty situation.
Using this condition, we eliminated the filtering required with the detection methods from previous work, and we gained the speed that is required to consistently detect all oscillatory fault cases.
In this novel approach, the two main steps in the detector have changed. We no longer generate the residual, as detection is now purely based on the observer error dynamics. Furthermore, instead of a threshold on the residual, we now have a condition on the observer error. And if this condition is violated, a fault is detected.
To show the capabilities of this novel detection method, we did Monte Carlo simulations. We have simulated faults at both fault locations over a range of different amplitudes and frequencies. Furthermore, we have simulated both liquid and solid faults, and we have investigated the effect of different input sequences on the detection performance. For each of these combinations, we have done 200 simulations with changing measurement noise, randomized parameter variation, and different turbulence conditions. First, we look at the fault type that has proven the most difficult to detect, which is the liquid fault at the highest frequency of 10 Hz. Here the fault is in the current commanded from the flight control computer. On the x-axis, we have a range of fault amplitudes, here in milliamperes, for which on the blue axis we show the detection time in number of periods,
where the median is shown as a line with indicators for the data points.
and a 90% region is drawn around it. Furthermore, the 3-period detection requirement is shown as a reference. On the red axis, the percentage of missed detections is shown in the form of a bar diagram. One can see here that after 1.1 milliampere, there are no more missed detections, and that the median detection time dips under 3 periods around 1.3 milliamperes. And at 1.6 milliamperes, over 90% of the detections are within 3 oscillations. Now, we can also show the effect of changing the fault's frequency. From left to right, we show the same results for faults of decreasing frequency. On the left, we see the same figure as in the last slide, accompanied by the results for 5 Hz fault in the middle and 1 Hz fault on the right. In general, we can see that lower frequency faults are easier to detect. 5 Hz faults can already consistently be detected within the 3 periods that's required, starting from 1 milliampere. And for 1 Hz faults, this happens at even lower frequencies. For the fault at the rod position center, the same simulations have been done. And directly in the first figure, with the results from the 10 Hz fault, we can see that also similar conclusions can be drawn. Here, at 2.4 millimeters, over 90% of the detections are within 3 oscillations. And again, for lower frequency faults, this will become easier. The figures supporting this can be found in the paper. We also did simulations with different control inputs. Here, we only show simulations for the 10 Hz faults with an amplitude of 1.8 milliampere on the left and 2.8 millimeters on the right. These amplitudes are chosen such that the detection without control input are comfortably within the 3-period requirement. We can see that with control input, detection becomes more challenging. And for the chirp signal, the median detection time even goes slightly above the 3-period requirement. The observation can be explained as with control input, the system uncertainty increases, and if the system uncertainty increases, the detection condition becomes less tight, causing a slower detection. Lastly, I will show the simulations we did for other fault types. Here we show only the sensor fault, where in the figure on the left there is a bias in the liquid fault, and in the figure on the right the fault is solid, so the fault replaces the original signal. In both cases, detection performance is better than for liquid faults. Also, this observation can be explained, as both the biased fault and the solid fault cause a larger overall deviation from the original system behavior, and this makes these faults easier to detect. In conclusion, we have considered the oscillatory fault case on an aircraft elevator servo, and we have designed a novel sliding mode observer based method for fault detection, which is fast enough to detect all the considered faults. This speed up of detection has been achieved by circumventing the filter that was needed to get the residual in previous work. With this novel detection method, all fault types could consistently be detected within 3 periods at all frequencies. For amplitudes above 1.8 milliamperes for the commanded current from the flight control computer, and 2.8 millimeter for the fault in the rod sensor. Furthermore, the design inherently guarantees that there are no false detections. Thank you very much for your attention, and we are happy to answer any questions you might have.